This is part one of my Neurips discussion. I attended Neurips last week in New Orleans, an unbelievably positive conference in many ways. I'm hopefully going to get more deeper throughout the parts. This is part one. I'm going to discuss a presentation by Chris Ree, where he introduced two important concepts. One is flash attention, and the other is using convolutions or recurrent neural networks to substitute for attention. And the idea in both cases is to lower the compute and memory budget in particular for foundation models. So this is going to be the first part. But before I go there, I'd like to just shortly maybe give a little bit of an overview for people that are interested. So Neurips is a conference that encompasses, how could I say, probably the best way to describe it is that academics and practitioners, in particular academics from all over the world, meet in one particular place, and they discuss all kinds of interesting new ideas as it pertains to artificial intelligence. Now, having said that, of course, there are many different ways to look at this. You have tracks where they talk about mathematics. You have tracks where they talk about, the ethics of foundation models. You have tracks where they talk about robotics. So it's very, very diverse in that sense, and that's part of the greatness of this conference. You can walk from one presentation where a statistical physicist talks about the sort of dynamics of models and dynamics of the mathematics that sort of, the trajectories of the mathematical functions that, go through a model and helps you understand how models work. Then you have a presentation about, let's say, cognitive psychology, where it's completely different approach, neuroscience. I think in a nutshell, anybody who's interested in the feedback, I can only recommend the conference. But having said that, I also have to say, absolutely, and this is maybe for most people obvious, but the more work you put into it, the more you're going to get out of it. Okay, if you just show up there thinking that you can sit there and learn, you're wrong. This is incredibly deep. It's academic, and academics don't have patience for explaining things to you as you were a 5-year-old. Maybe they should, but they don't, right? So the more work you put into this, the better. I'm doing a sabbatical now at Stanford and focus on AI. I mean, I'm doing all kinds of things, classes in English, in philosophy, but my focus is on engineering and in particular, artificial intelligence and robotics. So I was prepared. I had taken classes with people like Stefano Hermon, not classes really. When I talk about classes, think of it more like seminars, talks. I think I'm going to deepen a little bit. I'm going to actually take some real classes in the next quarter, but that's for another episode. Anyway, what I'm trying to say is I was prepared. I think I was really well prepared. I understood the problems of, let's say, attention models, which is going to be the first part of my talk here, which is the problem is the following. Okay, how can we reduce the compute and memory budget of foundation models? What are foundation models and what's the problem? This is, in general, what I'm going to discuss here. This is Not Even Wrong podcast. It's December 19th, 2023. This is Krim Delco. Since the last update, we're up 12.5%. The market is up 4%. For the year, we're up 125.2%. The market is up 24.2%. We're outperforming by 101%. Just before I go into the Neurips conversation, a quick update on the markets. I think in general, if you want to know what's going on in the markets right now, specifically, just look at the 10-year rates have come down quite a bit, or the 10-year values have gone up. And that's very good for the market. The lower, we don't have necessarily lower interest rates right now, but the expectations for long-term rates have come down. We have a downward sloping curve. The 5-year is 3.9, the 10-year is 3.9, the 30-year is 4. So in that sense, it's flat. But then we have the short term is 5.25. And then the 12 months is 5, and the 10-year is 3.9. So at least that is not inverted anymore. It's still not great news in the sense that we have a lot of problems, in particular the debt, and we at Orange Capital Partners are by no means, positive on the government and the debt and the lack of leadership, in particular under the Biden administration, is still very concerning. We believe that some of the, things like Texit, conversations like that, hopefully will spark attention, meaning if states like Texas, in Florida talk about secession, then that's a good thing. That's a good start. Not that we're secessionists in the sense that we want the country to collapse and end up in chaos or anything like that, but it's actually the other way around. We believe that the federal government and the federal budget and the federal administration is just completely out of control. There's no leadership. There is just a grab for all kind of mentality, and that's just not very healthy. In terms of actual fundamentals, I mean, Neurips was a perfect example of the beauty of technology, of engineering and applications. We believe there's a lot of economic value to be had. Chris Rhee said that in his presentation. Maybe just as a tangent, people like Chris Rhee really make me want to go to university. Like, he's optimistic, he's smart, he's concise, he's eloquent, but he doesn't oversell, right? He's really within the confines of, look, this is what I got, and this is where I stand, and this is what I expect. And he expects a lot of interesting new innovations, new value being created, and I agree with that. And that was my main impression from Neurips. We're at the cusp of a massive wave of value creation. Who's going to win and all that is, of course, that's the job of people like us to figure that out. We have bets on Tesla and NVIDIA as far as that's concerned. There's certainly other ideas. But we at Orange Capital Partners are more of a sort of large cap, traditional value creation type fund. We like dollar value versus percent value. So we're not necessarily interested in small companies tripling in value, but then going from 1 to 3 billion. That's just not our approach. We like the big caps because we believe that the big caps have the ability to translate technology and even science, in the case of Tesla, into products and services and monetize that. And that is sort of where we live as a fund. So the two aspects that Chris Rhee discussed are both in the realm of how can we make the systems more efficient when it comes to foundation models. So this is his fundamental idea of the talk. And the idea is that how can we make foundation models more efficient in training, and how can we make them more efficient in inference? This is the fundamental problem. And Chris Rhee, in his talk, he really he's very inspirational. I mean, this is tough stuff. If you read the Hyena paper, for example, if you read the SSM paper by Gu et al., if you read, generally, when you read these types of papers that deal with the problem, Flash Attention, where Chris Rhee was a co-author, Stefano and Ron and et al., those are incredibly difficult mathematical concepts. The fundamental idea behind both of these ideas, so Flash Attention and also sort of using recurrent or convolutional neural nets instead of attention, is to lower the memory budget. So what we want to do is not have to continuously go to all the previously related inputs and create this self-attention matrix, which is computationally very expensive and memory-wise very expensive. So the two approaches are, in a nutshell, Flash Attention deals with the memory budget, and the RNN/CNN, let's just call it legacy neural nets, let's call it like that, which is inspired by signal processing. They deal with both the compute and the memory. So let's talk about Flash Attention. What is Flash Attention? The idea of Flash Attention is that you can do block size work on a GPU. So you have a massive matrix, and you need to compute inner product or a dot product of two matrices. or you need to apply the matrix to an input stream of data. And because it's a massive matrix, you have to do a compute, move the data into another memory layer, because it doesn't fit on SRAM, which is the fastest and closest to the GPU. And you have to keep going back and forth and eventually make computation. And the idea is in flash attention is to do this in a way that we can do block-sized. So instead of doing line by line, column by column, row by row, back and forth, we do a big set of the matrix, we put it on SRAM, we do the math, and then we add another set of the matrix, so what's called tiling, and we find mathematical shortcuts, statistical representations of the results of the previous block, or the tile, let's call it that, that's what they call the tile. We find mathematical representations that conserve the information, but shorten the path and the memory bandwidth dramatically. And at the end, we get the same result, with much, much less memory bandwidth. This is the fundamental idea. These are some quotes from the flash attention paper. So current methods that like to reduce the computer memory budget of attention or transformers, and now quote, although these methods reduce the compute requirements to linear or nonlinear in sequence length, many of them do not display wall clock speed up, wall clock being the actual speed up of the whole computation, including everything, against standard attention, and have not gained wide adoption. So in other words, trying to increase the speed up and reduce the memory budget of transformers with other type of ideas has not really yielded any results. Now, quote, a missing principle is making attention algorithms I/O aware. That is, carefully accounting for reads and writes to different levels of fast and slow memory between fast GPU unchipped in SRAM and relatively slow GPU high bandwidth memory, or HBM, end quote. Our goal is to reduce the amount of HBM accesses. This is the main goal. The idea of soft attention, which is another word for flash attention, is to divide the matrix n times n into blocks, and then use certain math and statistics to track the results and sub-multiplications to eventually get to the right results. It's paramount that the blocks fit on SRAM and thus enable much faster calculation without back and forth between HBM and SRAM. Block sparse attention takes into account zero values, skips them, and thus improves performance, speed, and memory budget. So what I'm focusing on here is really more the idea and the approach than the actual technology, which I'm not qualified to discuss. I don't quite understand the mathematics behind flash attention. But what I do understand is that we can always find shortcuts in compute. Compute is the exercise of iteration, and you can always iterate over all the data that comes in. Think of machine learning as a signal processing problem. The signal comes in, you have an algorithm that is translating the signal into information, and that information can be used for predictive tasks. Now, the problem is you can always translate the signal one-to-one without losing anything, but that's computationally very expensive. A rock concert that needs to be compressed on a disc or to be a movie, a Netflix movie, has to be compressed in some ways somehow, so it can be streamed online. It's not possible. It's too much data in the actual analog movie, which a lot of people, like my friends in the movie business, say that that's important and that this whole streaming thing is stupid and blah, blah, blah. Now, the idea of signal processing in engineering has been around for a long time. And what Chris Ree et al. Are doing is use some of those ideas to improve machine learning techniques. And this is what's so inspiring about his talk. And this brings me to the next concept, which is RNN and CNN renaissance. Now, before I talk about Chris Ree's contribution, I want to mention Sasha Rush. Sasha has a YouTube talk at last year's MLSys conference. where he talks about the, recurrent neural net renaissance, more efficient RNNs, effective long-range parameterization. In his talk, Sasha explains research into RNNs that could approximate attention. So it's not like they're as good because they have a different architecture. The problem from a computational and memory aspect of attention is always, well, you're going back to a lot of previous tokens and you're collecting the relationship between those tokens through some filter and then making a prediction for the future. The idea of a foundation model is to try to assess the state right now and have a maximum likelihood estimation of the next state. This is fundamentally what they do. And the way they do it is through attention, and that's computationally very expensive and memory intensive. So what they do is in this RNN and CNN approach by Sasha, who heavily borrows from the SSM paper by Gu et al. And here's a quote from that paper. A key issue with attention layers, however, is that their computational memory costs scale quadratically with a sequence length. Chris Ree refers to this particular paper and a paper that they wrote as an inspiration from signal processing in how to deal with this problem. And in particular, their hyena model, which is the hyena paper, which they issued with a bunch of, Joshua Bengio and Stefano Emron and lots of other interesting people. What they say there is, you can think of, let's say, take a convolutional neural network. What is a convolutional neural network? Let's say go back to signal processing. You have a signal and you use a filter to compress that signal or to extract information from that signal that is not lost, but it's smaller or less computationally intensive. This is fundamentally what you're trying to do. You have a signal and you're trying to understand what that signal represents within the context of your task. In the case of pure compression, the task is simply compress, transmit over broadband, and then decompress, and people can listen to music online, Spotify. But in the case of machine learning, it's a little bit different. It's not about compression per se, it's about understanding what's in that information that can be extracted through eigenvalues and eigenvectors of matrices and then reapplied to new information. And you can, that's why it's called learning. You learn from the past information and you can make inference for the new information. And the signal processing is a cousin, not the exact same thing. But some of the ideas that have been around in engineering for a long time can be used here. One of the key problems is how to design state system models or recurrent neural nets, which are kind of cousins, and I don't want to go into details, the difference, but think of it like this. Instead of having this attention mechanism that always goes back to all the tokens, the previous tokens, you just apply a filter, and somehow, hopefully, that filter can have enough information from the past to then filter the new information to make an inference that is good enough to make a prediction or to do a task or whatever that may be. And if you can do that, you can gain a lot of computational and memory budget savings. This is the fundamental idea. The two big papers here, Gu et al. And then the hyena paper by Ree et al. I think are really just beautiful examples of how not everything needs to be thrown overboard, okay? Old engineering practices, signal processing has been around for a long time. So the question in the hyena paper, for example, is, are there subquadratic operators that can match the quality of attention at scale? We obtain a positive answer based on a composition of efficient subquadratic primitives, such as element-wise multiplication gating, and long convolutions, i.e. convolutions with filter sizes as long as the input. Now, the way they get these long convolutions is through parameterization of the convolution. In other words, they have computationally, they need less, the filters are less long because they parameterize. So they learn how to express the filter with parameters that then is equivalent to a filter that is as big as the data. This, to me, is the fundamental breakthrough here. So instead of using a filter that's as big as the input and therefore computationally not very efficient, we might as well use attention. You found a way to shorten, squeeze that filter and still keep the information intact. So to summarize, to summarize Christie's presentation, very inspirational. Foundation models are the Python to C++ for engineering and science. What he means with that, I believe, is that they will allow much faster, easier access, democratization of access to complex ideas, complex functions. I'm going to talk about the DeepMind approach of fund search and things along those lines, where you use foundation models to come up with programs and functions to solve problems. So you can kind of layer, almost have a deep deep foundation model. I don't know what you want to call it. So that's really interesting. And then my question to Christie would be, if I see him again, hopefully soon at Stanford, what ideas do you have for robotics? It seems to me like robotics is the chemistry of the 19th century. It was a distant cousin of physics. So this would be my first part of the Neurips conversation. It's Christie's presentation in how to use mathematical concepts to solve some of the system problems that transformers pose, in particular flash attention, which deals with the memory wall, and using RNN, CNN type models where you can use filters that are computationally a lot more efficient, that can use mathematical shortcuts. So those filters can be shortened, but still you maintain the same information. And the idea comes from signal processing. How can you filter a signal and still keep the valuable information of the signal and also keep the memory? This is important in machine learning. How far back do you want to go so you can then make predictions to the future? Thank you.